So good morning everyone. This is lecture number 19 EE211 analog circuit design. So we have started on differential amplifier and we understand what is differential means. So differential means it's 180-degree phase shifted to each other and it gives an advantage to have reduced or zero even order harmonics. This also reduced or makes it zero the common mode noise. And we also talked about two terminology. One is called common mode and one is called differential. Common mode is common to both the inputs, whereas differential is 180-degree phase shifted to each other. Now we studied this and we understood how it works and what are the things related to this one in previous few lectures. Now let's go to the next slide, which is on common mode. But in common mode there might be possibility that it's two terms, ICMR and OCMR. By the way, ICMR is nothing but input common mode range, and this is output common mode range. By the way, defining this is like, in general these are also known as CMR, common mode range. At any input also you can apply an input common mode range, or the ICMR is the minimum input DC or the common mode level which will not saturate the output after this level of input common mode reaches VDD or VSS. That's what we are calling it, ICMR. Look at this, the minimum. If you remember, we used to say that if this is a transistor, and we used to say that here it's actually V on plus VTH, and this side VTH will be down and this will be V on. So this is the minimum voltage which will make this transistor in saturation, or you can say that this is, if you remember, VDS said the minimum number we have decided to go around 250 millivolt. However, you can give more than 250 millivolt also and it will work. It depends on how much headroom do you have. So all these are also, this is also the input, this is input side common mode range, and this is the output common mode for a transistor. Do not worry, we are going to talk in detail about all these input and output common mode range, and there will be separate session on that. Maybe the next lecture will be on how to find out the common mode range, but before that there is most important part, how to find out the gain, which is common mode gain, and the differential gain. Okay, so this is what we kept it here, that input common mode range is the minimum input DC, wherever the output common mode range is the range of output DC values where the output does not get saturated, right? So these are the things taken from book, you can read that, and like these are the standard thing, but these are the most important part, as you are giving some common mode input from here and observing the output. So this value can be found out from the back calculation or from the value, and notably across each of the transistor, no matter what technology you are having, if it is 250 millivolt or greater than 250 millivolt, this works, and we call this one as VDS set. Some books are following V overdrive voltage, right? And the last one is V on voltage. So all are synonyms, by the way. Some books are like they have different notation, but they want to say the same thing. So note that. And I'm saying that value is greater than 250 millivolt. No matter what technology you're using, you are in safe zone of saturation mode of operation. Anyway, so let's go further, where you can see that there are two differential inputs and one common mode out input is given. Generally, this might be a DC quantity, but this is not compulsory, by the way. Sometimes we can use AC also, and AC can work as actually DC at a time. So in transient, each point, the sample point is acting as a DC, so, and that's going to bias this these transistors. Now, generally, when we are designing an amplifier, there are specific uh, things which you want to achieve, like the small signal AC gain you want to have as high as possible, and you call it infinite. Similarly, I need common mode gain, which we are going to call it ACM. It has to be as low as 0. So this is as high as infinity, this is as low as 0, and there is one term, as this is infinite or very high and this is 0, then CMRR has to be infinite, right? And as like common mode gain is as low as 0 and this is as high as infinity, means like your CMRR may be higher than differential gain. Notably, what is the AC gain? AC gain is the one where you want to, like, if this is an amplifier, there are two different things. So let's assume that this is common mode. So this is given to plus and minus, and this is minus plus, this is plus minus, this is V in, this is means. Notably, they are 180-degree phase shifted. These two are 180-degree phase shifted, and that's why this becomes V in and this becomes minus V in, and this is common mode voltage. So I want amplification of this small amplitude and frequency signal. I want this to get amplified. Generally, sensor inputs or sensor, whatever the sensor is producing, like temperature or humidity or any kind of sensor which is producing some signal, it's generally very small by nature. So people are using amplifier whose amplification is very high, as high as infinity, right? We want to see the signal, sound signal or any kind of signal, you want to amplify it to the highest value so that it does not get saturate to VDD or VSS. Notably, it should not be going beyond these two values, and that's why, like, it's small signal. If it is beyond this, then it's large signal. So we have to make sure that you are in the small signal. So this is what we want to amplify. However, we don't want this common mode value, let's call it VCMI, for input common mode voltage. I don't want to get amplify a lot, means, although like you cannot stop that, what I mean to say is that, let's assume that this is VDD equal to VDD and VS is equal to 0. So you have, so this is VDD and this is VSS. So your output cannot go beyond this one. Moreover, let's assume that this is VCMI, and on top of that you are applying the small signal input. Now what is happening here is you cannot stop this. VCMO is getting shifted somewhere, and something like this. You will have, this is output and this is input. So here you can see you want this amplitude as high as possible. Some people are choose to use DSO setting with AC as one of the setting. However, it is desirable to use the DC setting for the probe. However, if you are using AC, then what is going to happen? This VCMO, VCMI will not be seen. However, it will come to directly to the ground in the AC setting of DSO. So if this is an input, the output may look like this one. And sometimes what happen, you will see something like this and you will see that, oh, this is not working, and you're complaining. This is not VDD, by the way. Some value but not VDD. Okay. So this is amplitude with respect to time. So it's getting saturated. So it's a bad design, right? But you forgot to see the DC setting. If you see the DC setting, then you will see that there is one extra component or the DC term which is going to be added over here, and that might be the reason to get the saturation. The major problem is because of the DC term. But in the ideal condition, I don't want that to get shifted, which is the actually common mode gain over here. I don't want any difference between input common mode and output common mode. So it has to be as low as 0 or VCMI equal to VCMO. Then things will be fine. And if this is equal to VDD by 2, I'll be happy. The most happy guy, because there is no fluctuations in input common mode to output common mode. But that's not possible. That's not possible. There has to be some number. So that's why I'm saying I'm expecting to have the common mode gain as low as 0, but there'll be some gain, right? So notably, like this gain might be like 6 dB, minus 6 dB or minus 10 dB or something like that, or sometimes little bit higher than 0 dB. So it depends on your circuit. And similarly, like this small signal AC gain, you are expecting to have as high as infinite, but that's not possible, right? It will be in the range of something like 60 dB or something like that. In the case of op-amp 741, if you know, it's common mode gain and all these things are in the like AC gain is in the range of 60 dB, CMRR is around 60 or 70 dB, and accordingly you have the common mode gain. So these are the important aspects of any amplifier to get designed, right? On top of other things, like of course there will be frequency domain analysis will also take care, and you have to add UGBW as well, right? Anyway, so let's move to the circuit which has following circuit. I want to find out, my agenda is to find out differential gain and common mode gain. If I need these two, and if I have a circuit so this is a differential circuit, where there are two inputs. Let's call V in plus and let's call it V in minus. By the way, where V in plus is nothing but V in, or let's call this one VCMI plus V in, and V in minus is nothing but VCMI minus V in. So this is 180 degree phase shifted AC signal, and these are the common mode inputs which are going to take care of these two transistors. Notably, when we are making the differential circuit, it's very important that both the balance networks are identical to each other. So balance network 1 and balance network 2 has to be identical, because that is very important thing. If they are not, then you will see some difference, and we are taking the output from middle of. So this is V out minus and this is V out plus. I'm making the different notation because this is common source amplifier. When we are saying this identical, what we are saying that GM1 equal to GM. So if these two are, let's call it RD1, RD2, M1 and M2. GM1 equal to GM2 equal to GM. RD1 equal to RD2 equal to RD, and RO1 equal to RO2 equal to RO. Right? So these are the known thing to us when we are making the differential circuit, right? So if we are doing this, what is going to happen? If you remember the initial lecture, maybe uh, lecture number 16 or 17, where I talked about if there are two balanced networks, they are connected with a common link which is here. And let's call this one as VP. No matter what I'm connecting here, it's going to be at ground, which we are calling the AC virtual ground. And this happens when there are differential signal, or one side is plus V and one side is minus V, or the 180 degree phase shifted things will have such things. Otherwise this is not going to happen. And if this is happening, you can treat both the circuits as pseudo differential, or you can find out the balance network 1 and balance network 2's V out in terms of V in, and you can write down the equation directly, the gain equation. So for the balance network 1, let's find out V out minus in terms of V out plus. That becomes minus GM times RD in shunt with RO. I'm writing this because of this assumption, right? Times V in plus, and V out plus, which is for balance network 2, it's again minus GM times RD in shunt with RO times V in minus. Combining both of them, if I take the difference of balance network 1 and balance network 2, I am going to have whatever way you want to write it down, no problem. Right? So this is what is happening over here, and you're seeing this gain. It's similar to what you were achieving at the single ended. However, here the input and output are difference of two different terminals, and that's how you're getting the double input, or the fundamental quantity is double, second harmonic is double, third harmonic is double, everything is double over here, because you are taking the difference of these two. When you are taking the difference of these two, this becomes, so if this is plus V and if this is minus V, if you are taking the difference of two, it's going to be like this, something like this. So this is what the input is now, right? So you can see here in my slides that there are two balanced networks. I found out that I found out that in the presence of in the presence of differential input signals, outputs are also differential or 180-degree phase shifted, and this potential Vp goes to virtual ground or the AC ground when V in 1 equal to minus V in 2. So you can close one of the circuit, and this particular concept is known as the Hopf circuit. Sorry. So this is known as the Hopf circuit, where you're keeping one circuit as close one, and then you are finding out V in with respect to V out, and again you are doing it for other circuit and you are finding out what is V out in terms of V in. You can see that you can see here. So whatever the gain we got it here, which is same gain you are going to get, and this is closed. What is going on? There's some problem here. Right, and when you open it you can have the gain. So notably both side the gain is equal if both are identical, and when you take the difference the gain is the same as what you got here, right? So it's minus gm times rd in shunt with ro. That is going to be seen in both the time, right, or both the condition. This is what we are calling it Hopf circuit. However, you can see that if it is same gain, there is no need to look at the other side, and you can declare directly that this is the differential gain. Notably, when you are taking this, it's actually input is getting doubled, right? So that is more important insight over here. So differential gain is similar what you got it in the case of single-ended. However, the input range getting doubled. Now let's talk about the condition when both the inputs are not differential, because we are applying the superposition and we are checking we, we are checking what if I am applying here input common mode voltage or both sides same input. If this is the case, now in this case, if these are two identical balanced network, as we know that we are going to do it in differential circuits. So balanced network 1 and the balanced network 2 are identical and similar. So in this case, from here to here, this is a common mode voltage. Notably, it's not the differential or the sine wave where you can apply the previous theory. However, if this is increasing, if you remember, in the case of even BJT also, what you want, if this is VBE and VCE. If you want this one in the active mode of operation, VCE will be higher than VBE. And notably, base to emitter and base to collector junction are actually like base to emitter is forward bias and base to collector is reverse bias. So in that case, VCE has to be more. This potential has to be more than this one to get this reverse bias. So in case of VB to VC, VC was always high. Similar to that, this VDS is always higher than this potential. So if this is increasing, this will increase a bit to get this transistor in saturation mode, because this VDS set is nothing but VGS minus VTH, so it has to be higher than that. So VGS is playing role over here to achieving the common mode voltage of, or the voltage across any transistor. It's affected by the input transistor. So now if that is the case, if this is increasing, this is going to increase, by the way. If this is increasing, this is going to increase. So both are in same direction, right? So if this is plus, this is plus, this is plus, this is plus. But notably, when this is happening, if this and this both are same, then these and these both are same. So let's call this one as V out plus and V out minus. I need to write down maybe in capital just to make sure that what I'm doing is. So here, as V in plus is equal to V in minus equal to V in, V out plus equal to V out minus equal to V out. So let's keep this thing one side. Okay, this is one part. The second part is saying that the potential VP, what will happen to potential VP? It's not going to be zero, because both are connected to same potential. If there are two balanced network which are supplied with inputs which are identical to each other, plus V and plus V, you can say that the current flowing through these two are equal, and here the current flowing through this one will be 2I. That is what you can say, but you cannot say that this VP is equal to 0. Of course, it's not going to be 0. So VP is not 0. If VP is not 0, you cannot say like a previous game that you make it 0 and let's make it pseudo differential, which is acting as a single-ended amplifier. You can directly say that minus GMRT. You cannot say that. So VP is not equal to 0. In that case, it is very important that what value of resistance is, or what is the resistance over here, you need to find out. And for that, you can just write down RSS for the case of current, because you know that any current mirror you are designing, its output impedance will not be infinite. This is unfortunate, but that is the fact, right? If this is going to happen, and on top of that, there is third theory which says that if two nodes of a circuit are identical or exactly same, you can consider those two nodes as the short circuit, right? So this is important theory. So I found out that V out plus and V out minus are equal, as V in plus and V in minus were equal, so they were identical, and that's why like we were shorted them. So let's short them. By the way, this is happening on a notebook. This is not happening in reality. So when you are doing this, there will be some difference, by the way. Look, it's very difficult to get M1 and M2 identical, RD1 and RD2 are identical. However, on paper, we are saying that GM1 equal to GM2 equal to GM2. and we are saying RD1 equal to RD2 equal to RD, and we are also saying that RO1 equal to RO2 equal to RO, but there will be some delta change. There might be some delta change. There might be some delta change. Right now we are not considering that. If those are there, then these two are not shorted, but we are saying that it's identical right now for a time being, and let's make the complete ideal condition. So in that case you can redraw this circuit as follows. So what you can do, look at this. This is MVP, and here M1, right? So this is what happening if I redraw the circuit. Still I am interested in V out by V in, which is common mode voltage, by the way. So you can simplify this as, if there are two transistors in shunt, and each of the transistor is going to give you 1 by gm of resistance. If you are keeping two transistors in shunt, that's going to give you 2 by gm, right? And notably, when there are two channel length modulation resistances in shunt, they are making actually effectively RO by 2. So GM becomes double 2 by GM, and this becomes RO by 2, right? So this is already, we got it for these two transistors. Here RD1 and RD2 are exactly identical, and if they are equal to RD, then this becomes RD by 2. However, RSS will not going to change, as this is already common to both the places. So we have done this one only. So in that case, if I am asking you to find out V out by V in, which is a common mode gain, so then the common mode gain is equal to, as this is going in positive direction, you can find out what is the output impedance. It's RD by 2, first of all, which is looking at this side, right? And from here it's 1 by GM, actually 2 by GM plus RSS. However, if you are interested in keeping the value in shunt, you can keep those things also, like you can solve it. I'm keeping up to you that what I'm going to see. So that's what you can keep it here, right? So that's the common mode gain. If there is no channel length modulation, this is the common mode gain, right? If you want to simplify, you can simplify as follows, like GMRD divided by 2 plus GMRSS, right? Or you can write down GMRD by 2 1 plus GMRSS by 2, right? So you can simplify and you can write down. However, the common mode gain is this one, right? Notably, when we are doing this, the V out is higher than V in. That's why, like, we are keeping the plus sign over here. If you want to check on maybe using the analysis KCL KVL, you can check that it's going to be positive. Now so these are the standard things, and you can find out parallel matched all these transistor, and you can find out the common mode gain. Now, if I am giving you few examples to find out the differential common mode gain and CMRR. By the way, in this case, notably the CMRR is nothing but differential gain, which was minus GMRD divided by the gain which we have achieved over here. Because this was source degeneration, that's why like that is the resistor. So this is the CMRR or the common mode rejection ratio. Common mode rejection ratio is nothing but differential gain divided by common mode gain. By the way, if I am asking you to find out the CMRR of a single-ended circuit, then it's very easy that differential gain and the single-ended gain both are same. First of all, in that case, right? The single-ended gain, whatever you are seeing, both will be same because it's with respect to 0. However, in the case of common mode gain and differential gain are equal because you are giving differential as well as common mode at the same place, so both will be same. So if both are same, then CMRR equal to 1 volt per volt, or you can say that 0 dB, right? That might be sometimes people are asking for the quick knowledge in interview, right? So you can answer that. Anyway, if I need to find out three terminology: differential gain, common mode gain, and CMRR, let's practice that over here. So in this case, we know that I can apply a Hopf circuit concept where M3 equal to M4 equal to, let's call it M3, M1 equal to M2 equal to M1, let's call this one. What is the meaning of this? Means GM1 equal to GM2 equal to GM1, GM3 equal to GM4 equal to GM3, and similarly you can write down for RO and like RO also, right? So let's forget that because we agreed that both the networks are equal. In that case, this particular wire is connected between two networks. You can call this one as AC virtual ground. If you can do that, and if both the circuits are identical, you can find out the gain from any one of the circuit, and you can directly declare that this is differential gain where the input is actually getting doubled. So in that case, what is the gain? The gain is very easy. You can write down minus GM3, sorry, minus GM1 divided by GM3. Even though there are some channel modulation, it's going to be removed because GM is much lower value than RO. So this is the differential gain. Now we are interested in the common mode gain. So in that case, what is going to happen? Both the inputs are identical. If these two are identical, of course V out will be identical. You can short them. You can. And on top of that, this Vp is not equal to 0. And let's assume that the resistance offered by this current is RSS. And you can redraw this circuit as follows: M3 and M4, which are identical to each other, going to be in shunt. Yeah, so this is going to happen. I cannot write down to M3 because this is going to happen in the case of GM only. And if I'm taking the output from here, what is the common mode gain? Common mode gain will be coming from here. It's nothing but a simple one. Looking upside, it's there are two transistor diode connected which are in shunt, so each one of them is giving you 1 by GM, so it will be total in 2 by GM. Looking upside, looking this side, sorry, you can find out, but right now we are avoiding the channel and modulation, other things. So looking from here, as this is source degeneration, this is becoming 2 by GM 1, let's call this 3 plus RSS. So the common mode gain is nothing but 2 by GM3 divided by 2 by GM1 plus RSS, and the CMRR is nothing but ratio of these two. I hope I have not made any mistake, or so the ratio of these two. Yeah, so that was correct actually. And is GM1 times 2 by GM1 plus RSS divided by GM3 times 2 by GM3. So this is gone, so it's effectively mod of this one is going to be equal to GM1 times 2 by GM1 plus RSS only divided by 2. Right? So you can see the dimension wise, like it's everywhere it's unitless. Yeah. Now let's go to the next part, the uh, second example, where you can find out the differential and common mode gain. So now differential gain, this is known to us, both the identical network are there. So mod of differential gain, now I'm avoiding making the sign. This is ground, so I can write down directly minus GM1 times RO3 in shunt with RO1, right? Notably M3 equal to M4 equal to M3 and M1 equal to M2 equal to M1. This is what I'm considering. In the case of common mode gain, this potential is not going to be at ground, but this is going to be given by RSS. So you can write down that, so two transistors are in shunt, M1 and M2, so it's M1 plus M2 which are equal to M1, so it's 2M1 and this is 2M3. In that case, what I'm going to see, I'm going to see as follows. The output from here, it's RO basically, so it's RO3 in shunt with RO3, which is going to make it RO3 by 2 divided by 2 by GM1 plus RSS, right? And you can write down CMRR very simple way, GM1 RO3 in shunt with RO1, or you can write down this divided by this and you can simplify. There is no doubt about that. Now, so this is already, so now there is a next circuit which is actually the cascode, and you need to find out differential gain and the common mode gain. So if this is differential gain, we know that this side is identical to the other side and I'm applying 180-degree phase shifted uh, input, then this becomes virtual ground, and I can write down the differential gain equal to nothing but minus gm1 times, so this is the output side. I'm going to see gm5 ro5 times ro7 in shunt with gm3 ro3 times ro1, right? So this is your differential gain. If you take it mod, it's the sign will not be there. For the case of common mode gain, it's similar, but the only thing is Vp is not equal to 0, and this current mirror is going to give you some resistance called RSS. While doing this, you need to find out. So common mode gain is nothing but, I can write down here so that I can write down the complete term. Common mode gain is nothing but, so this side it's 2 by gm plus RSS, that will be there. But by looking at these two sides, I'm going to see following things. So this is, by the way, this circuit is applicable to differential one. So, and this case it's like this: m1 plus m2, m3 plus m4, m5 plus m6, and m7 plus m8. m7 and m8 are equal, so the contribution of gm becomes 2 by gm7, and ro becomes ro7 by 2, because 2 ro are in shunt. In this case, if gm is there, it's 2 by gm5, and if it is resistance, it's ro5 by 2, because two channel and modulation resistance are in shunt. Notably, like all these points are shorted. So that's how, like, everything getting in shunt. And this one is also going to give you 2 by gm3 if gm contribution, and ro3 by 2, in this case 2 by gm1 and ro1 by 2. This is what we are writing with the fact that m7 and m8 are equal, and it's going to be equal to m7. m5 and m6 are equal, and that's going to be equal to m5. m3 and m4 are equal, and that's going to be equal to m3, and m1 and m2 are equal, and that's equal to m1. And we are writing the equal contribution in terms of gm and ro, because that is what going to happen. So in that case, if I need to find out the output resistance, now I need to see this side and I need to see this side. So it's a cascade connection. You can see if it is upside, it's going to be equal to generally gm5 times ro5 times ro7. That's the case when it's actually just m5 and m7 are there, but there is m6 and m8 are also same, and it's identical to m5 and m7. Then gm becomes double, ro5 becomes half, and same thing is going to happen this side. It's gm3 which will become double, and this is ro3 divided by 2, and times gm1 which is double, and ro1 divided by 2 times rss. So I can write down here, it's 2 gm5 times ro5 by 2 times ro7 by 2 in shunt with 2 gm3 times ro3 by 2 times 2 gm1 times ro1 by 2 times rss. So depending on which quantity is higher, of course this quantity is higher, so it will be dropped, this side will be dropped, and you're going to have, this one is your common mode gain. And taking the ratio of these two is going to give you the CMR. The ratio of these two is going to give you CMR. Now there might be one more question which is popularly asked in many places. So in this case, if we are talking about the finding out the differential gain, look at this. These two networks are identical to each other. What I mean to say is M3 equal to M4 equal to M3 and M1 equal to M2 equal to M1, and the related parameters are same. So accordingly you can write down the things. In that case, it's going to be equal to as follows, that these two networks are connected by a wire whose node value is Vp. So if you are applying here V in 1 equal to V in 2 equal to, like with 180-degree phase shift, then this potential goes to 0. If that potential goes to 0, you can use the Hopf circuit and you can find out the gain from either of the side, and you can call it differential gain. So then it's equal to gm1 times, let's call it 1 by gm3. So this is gm3, right? Now if they are not differential input, then Vp is not going to be 0. You can, okay, by the way, while doing this you need to understand that this is potential X and this is potential Y. I forgot to include this one. So if this is potential X and this is potential Y, and if this is R, what I can do, I can make this one equal R by 2, R by 2. This is just to understanding part. This is what we are doing. And X side, you know that this potential X and potential Y, as this is small input which is differential, at the output side you are going to have the amplified version, but you are going to have the 180-degree phase shifted X equal to minus Y. You can say X equal to minus Y, or if this is like this, this is going to be like this. In that case, these two are identical network or the balanced network. Let's call first number balanced network, let's call second number balanced network. And in that case, what you can say about the line which is connected in between these two networks are its ground, or you can say that it's AC virtual ground. And if this is the case, you can redraw this as follows. So there is a ground, and this one you can call it R1 by 2, R1 by 2, and it's connected to virtual ground. So at the node X and Y, by removing this R1, you have extra resistance whose value is R1 by 2 and R1 by 2. So now, like, it's coming into the picture of both the networks, and those are identical to each other, and this potential and this potential are also AC virtual ground. So in that case, what is going to happen? Then the output resistance will be changed, and that's going to be equal to 1 by gm3 in shunt with R1 by 2, R1 by 2 in shunt with R01, but I don't taken into account. I assume that it's much higher than 1 by gm3, so 1 by gm3 is winning, and R1 by 2 depending on the input side, and this is going to be equal to 1 by gm1. So if R1 by 2 is much higher than 1 by gm3, then the answer is gm1 by gm3. However, in the case of other side, the answer is different. Now let's talk about the case when we are talking about the common mode gain. So we found out the differential gain, no problem. The differential gain, we can keep it here somewhere. But in the case of common mode gain, we know that if we are shorting these two, where M1 and M2 are equal, This is also shorted, and notably this is also going to get shorted. So in your analysis, R1 will not be there in common mode gain because it's connected in between. Even if you're connecting one big op amp or anything, it won't be coming into picture, right? So in that case, if I want to find out the gain, what I'm going to see, I'm going to see as follows, that the output looking upside and the downside, there are two resistances, where the downside it's a cascade connection of these two, so it will be much higher than looking into upside. So I'm going to only taken into account the upside resistance, and upside there are two diode connected things which are in shunt. So 1 by gm, 1 by gm in shunt, so 1 by gm and 1 by gm in shunt is going to give me 1 by 2 gm, right? So it's going to give me 1 by 2 gm. That was one mistake, I made it here. It has to be 1 by 2 gm5 and 1 by 2 gm7. Sorry, it was a mistake. You have to keep it into account. 1 by gm, so 2 1 by gm in shunt. So that is going to give me 1 by gm3 times 1 by gm3 divided by 1 by gm3 plus 1 by gm3, right? Sorry, not 2. So that is going to give me 1 by gm3 divided by 2. So that is going to be given by 2 by gm3. So it was a small mistake. So please make sure that it's 1 by 2 gm, and RO is also there, but 2 RO is much higher than 1 by gm. So this is going to be like at the advantageous side. If you want to keep other things also, then you can keep RO 3 by 2 also if you wish to do, right? If you are looking up, downside, looking down, it's a cascade connection, it's going to be very big number. If you wish, you can write down that also, but like the simplified answer will be this one, right? Or you can even drop this one if RO3 is much higher than 1 by gm3, right? And you can write down the complete common mode gain as follows. It's looking into this, it's, by the way, resistance offered by this current mirror is RO5, where V bias is bias voltage. So RO5 plus 1 by, so 2 gm quantities are in parallel, so it's going to be 1 by 2 gm1, and looking upside, it's 1 by 2 gm3. If you wish to simplify, you can simplify, and the common mode rejection ratio is nothing but a ratio of these two quantities. But here the main catchy point is the resistance in between. So if there is a resistance in between, or any inductor, any impedance is in between, you can apply the AC virtual ground concept and you can find out the values. And this is the case for uh, this is the case for AC analysis, or the differential analysis. If it is common mode analysis, then in that case, both the potential x and y will be same, and that hence both will be shorted together. So there is no point in keeping anything other than that. You might have the circuit which looks like this one. If there is a circuit which looks like this one, which has, okay, maybe I can draw in the clean one. If there is a circuit which looks like this one, so let's assume that I am applying the gain boosting to this A1. So in that case, in differential, you have to take it the Hopf circuit approach. This is going to be 0, and in between this transistor A1 there will be ground, and you have to consider that one, right? But in the case of common mode, this will be shorted together, so it's not going to give you any impact. Or similarly, this is also shorted, so it's not going to give you any impact, right? So remember this and apply uh, this theory accordingly. I'm not going into other things, but rest of the things we can talk maybe in the next lecture. Thank you very much for today.